Okay, in this example, we're going to differentiate this relation graphed in front of you here, x squared y minus y cubed equals 1. And we're going to pay particular attention to those white ordered pairs graphed in front of you here. And at those ordered pairs, the tangent slope is going to be absolutely vertical. So the tangent slope is going to be undefined. So the question is, how do we determine the exact coordinates of those 2 points where the tangent slope is undefined? Okay, so we're going to differentiate this relation. Of course, we're going to use implicit differentiation. And before we do that, just as a reminder, that y, if we got it by itself, would be in terms of x, so we have to treat it as a function of x, using that term a little loosely. So now, if we think of y as a depending upon x when we differentiate both sides of this equation with respect to x, we treat y as a function of x. So our derivative, we're going to require the product rule for the first term. It's going to be the first x squared multiplied by the derivative of the second, which is y prime of x, plus second function multiplied by the derivative of the first, which is 2x. And that was just the derivative of our first product there. And now after the subtraction, we have to use the chain rule. So we deal with the power first. We have a trapped y of x function. Our power goes down to 2, and then the chain rule forces us to multiply by the derivative of that inside function. And then the derivative of 1 is 0. So we scroll through our mess there, I guess, and we look for y prime of x, and we isolate anything with the y prime of x in it on the left-hand side of our equation. So that would mean we keep x squared times y prime of x on the left, and also that minus 3 times y of x squared times another y prime of x. So all we're really going to relocate is that y of x times 2x. And make sure I change the sign on that, of course, as we subtract that from both sides of our equation. Okay, so at this point, we're going to drop our y of x notation and y prime of x notation, which we could have easily done already. And then we'll work on our common factor. So this is going to be 3 y squared, y prime. And then over here, we might as well alphabetize as we're recopying that. That's minus y times 2x, or minus 2xy. And now we can pull out our y prime common factor. And we're going to have x squared minus 3y squared in brackets once we factor that out. And now lastly, to get our derivative, we're going to divide both sides, of course, by the expression in brackets, x squared minus 3y squared. And on the top, we got minus 2xy. Okay, so now that we have our derivative, we have to figure out a way of making our derivative undefined, or finding out a way of making the denominator of our derivative equal to 0. And in order for that to happen, x squared minus 3y squared would have to be 0. And another way of thinking of that, we would have to make x squared exactly the same as y squared, 3y squared. So the difference of those two things is actually 0. Now this equation by itself is not going to allow us to determine where our vertical tangents are happening. We have to substitute this information back in our original relation. Okay, so if we go back to our original relation, x squared y minus y cubed equals 1, and we, I guess, make this stipulation that x squared has to be 3y squared, we can see there's an x squared in our original relation, and we can sub in, I guess, our stipulation here in place of it, that x squared must be equal to 3y squared. So since there's two variables in our derivative, we have to rely on two pieces of information in order to deal with the two variables. And of course, our second piece of information is our starting point, the actual relation that we differentiated. So if 3y squared is equal to x squared, you can see now we have an equation that's entirely in terms of y. And if we multiply 3y squared and y, we will get 3y cubed. And then we subtract y cubed equals 1. And we have like terms miraculously. This is going to give us 2y cubed equals 1. And that would give us y cubed equals 1/2. And I guess I'm going to have to scroll down some. And then to finish that off, of course, with a cube root on either side of that equation. So therefore, the y value, of which we will find these elusive vertical tangents, would be at the cube root of 1/2. Okay, so those are our y values of those two coordinates that we saw at the beginning of this video. Now, of course, how do we find the x values? Well, we still have our first equation here that we can go back to now. That if y is equal to a cube root of 1/2, we can go back and say that x, if I can get my pen activated here, we can go back and say, well, x squared would have to be 3 times those two y values, or sorry, that y value, all squared. So we can sub in that y information into our first equation again. And this is going to be the cube root of 1/2. Okay, so now that we've done that substitution, we can find our x values by trying to solve x squared equals 3 times the cube root of 1/2 all squared. And that's a mouthful and a brainful as well. But on the left-hand side, we see a square. So that would mean we need a plus or minus square root. That's somewhat familiar territory. Now, the bad news is we have to deal with all this stuff. I guess I'll write that in white. We still have that cube root of 1/2 in there. Write that way for a few more steps. And now if we take the square root of a product, and we do have a product, x squared is a product of two things, then we can break that product apart with a pair of square roots. And that's probably the easiest way to deal with this mess. That would be the square root of 3. Multiply the square root of a square. So the square root, and I guess I can write this out in one more step, the square root of a square, and inside that square is our little cube root of 1/2. I think you can see there that square is going to get rid of that square root. I guess I should say the square root is going to get rid of that 1/2. So I can write this as x equals plus or minus square root of 3 multiplied by, all we're left with is our white cube root of 1/2. And I think at this point, clean this up a little bit, we can take the cube root of the numerator and the denominator, and we have our x values. We'll have plus or minus square root 3 multiplied by the cube root of 1 is 1, and in the denominator we'll have the cube root of 2, which of course we'll leave as the cube root of 2. So you can multiply those two things together and stack them up. So our x values, finish off our coordinates here, are going to be at plus or minus square root of 3, all divided by the cube root of 2. Okay, so here we are back in Desmos. We'll let Desmos deal with the decimal representation of those numbers. So I can unhide my folder here, and you can see there are two ordered pairs, lots of radicals and lots of roots, but there they are. And you can see, of course, they're plotted on the graph. And right at those locations, we could form some vertical tangents. And why don't we label those so you can see the decimal representation. It's probably a little less intimidating that way. And lastly, let's just plot those vertical tangents so you can make sure you're clear with what we found. So if I say x equals, I'll just go up here and do a copy and paste. Take that one first. There's a vertical line, and our second vertical line will be that positive value. And I guess we can clean up the colors here. There's our two vertical tangents, and you can see that, yeah, those lines seem to be tangential to the curve at those two ordered pairs, and they are definitely vertical lines. So our algebraic magic worked, and there we've identified the exact coordinates of the vertical tangents for this relation.